In this module, we are going to prove a somewhat technical result called the Baire Category theorem. We will use this result in studying the structure of the discontinuities of a function, but the deeper applications of this result can be only seen in a future course on functional analysis. So, without further ado, let me just state a definition which is long pending. Definition: a subset A of R is said to be dense if A closure is equal to R. Immediately we have examples way back from week 2 that Q, the rational numbers, and R minus Q are both dense. Well, proof. What we call density way back in week 2 was slightly different from this definition, but you will be able to show quite easily that both Q and R minus Q are dense. Okay, so let me state the Baire category theorem and prove it. The proof is not too hard. In fact, the proof that I am about to give is very similar to the proof of the uncountability of R that we saw using the nested intervals theorem. Let Gn subset of R be a sequence of open and dense subsets. Then G defined to be equal to intersection of Gn is also dense. So if you take a bunch of open and dense subsets, then the intersection is also going to be dense. Proof. And please, after going through this proof, look back at the proof of the uncountability of R using the nested intervals theorem that we saw and look for the similarities. So let x0 be an element of R and let I0 subset of R be any closed non-singleton interval that contains x0. Okay. Now, because G1 is dense in R, G1 closure is equal to R. This is the very definition. G1 closure is equal to R. That means there is a sequence xn in G1. Let me not use xn. You will understand in a moment why. There's a sequence yn in G such that yn in G1 such that yn converges to x0. That's because that's the definition of closure. Okay. This means that for large n, yn is an element of I0, right? Because the sequence yn converges to x0, for suitably large n, yn must be in this closed interval I0. Okay, this means G1 intersect I0 is non-empty. Okay. In fact, note that this is true for any interval. And note that this is true for any interval. Okay, this is just a side remark. What we have shown is if you take a dense set, then intersection of the dense set with any non-singleton interval will definitely be a non-empty set. Okay. Now, how is this useful? Well, look at interior of I0. Intersect G1. By a similar argument, this is also going to be non-empty. Okay. Essentially, what we used in the previous argument is the fact that for suitably large n, yn will belong to any given interval of x0. So in particular, this taking it to be an open interval gives no additional difficulty. Okay. But both of these are open sets. Both of these are open sets. Okay. This means interior I0 intersect G1 is an open set. Because intersection of two open sets is an open set. Okay. Now what we do is we can find a closed interval, closed non-singleton interval I1 that is contained in interior of I0 intersect G1. Okay. Now since G2 is dense by exactly the same argument, notably what is there in the parenthesis here, since G2 is dense, we can repeat the same argument to find a closed non-singleton interval I2 such that I2 is contained in interior of I1 intersect G2. Okay. In fact, if you think about this carefully, because I1 is actually contained in interior of I0 intersect G1, this I2 is also going to be a subset of interior of I0 intersect G1 intersect G2. Okay. Similarly, we can find closed non-singleton intervals I1 containing I2 containing I3 ... such that In is contained in interior of I0 intersect G1 intersect G2 ... intersect Gn. Okay. Excellent. But intersection of In is non-empty by nested intervals theorem. Okay. This just means that the intersection of Gn is also non-empty. Okay, is also non-empty. Okay. Now, how does this help us? Well, note that intersection of Gn intersection interior of I0 is also non-empty. Simply because each one of the intervals is contained in I0. That's how we had constructed these. So what we have shown is this set G intersects I0. Okay, but I0 was an arbitrary interval, right? It was just an arbitrary interval. We didn't put no hypothesis on I0. I just said let x0 be in R and let I0 be subset of R, be any closed non-singleton interval that contains x0. That's it. So, but I0 was an arbitrary interval that contained the fixed point x0. Okay. Now what does this show us? This shows that no matter what point x0 you take and whatever small interval around that point you take, there is an element of G that is in that interval. So this shows that that G is dense in R. Okay, I have done most of the work. Just from concluding that G is dense in R is an easy exercise. Easy exercise. Okay, so this concludes the proof of the Baire category theorem. Now, usually the Baire category theorem is stated in a somewhat different way. Let me just state it, but I will not elaborate on it because it starts to get a bit technical. A set S subset of R is said to be nowhere dense, if interior of S closure is empty. Okay, so we say that a set is nowhere dense if at no point does it accumulate an entire interval. Whereas a dense set is something that accumulates all intervals. This is something that does not accumulate any interval. The terminology is a bit weird, but you will get used to it when you are in a more advanced course. So there is another form of Baire category theorem, another form of Baire category theorem that states the following. The set R cannot be written as a countable union of nowhere dense closed sets. Okay, and the proof is left as an easy exercise for you. This will be just translating terminology and using the previous version of Baire category theorem. So proof is easy exercise. So I'm being a bit quick because this is in fact a theorem that is best taught in a later course, but nevertheless we need it as a tool in one of the theorems to follow. So please don't focus too much on this theorem. There is a time and a place where you will get a chance to understand the intricacies of the Baire category theorem. This is a course on real analysis and you have just watched the module on the Baire category theorem.